All right. So I'm Tim Bess. I'm the software architect at Bluechip Financial. And Tim, I'm going to be talking about how Statefun, Flink Statefun can be used to essentially approximate the actor model, but in a polyglot way, so that you can use multiple languages to work together within that actor model. So, first of all, what is the actor model? So, essentially, there are three major concepts that you need to know about. There are actors, which are essentially little processes that have an inbox. They can receive messages. Those messages cause them to mutate their state, usually, or send other messages. Their state's usually ephemeral, like a regular process. You can persist it, but again, it's sort of on the end user to manage that. And there's usually some sort of supervision is the point of using this. So essentially, if you need to do some work, an actor can spawn another actor, supervise it, and send it a message. And if it succeeds, it'll get a reply. If it fails, it will get a notification from the actor system itself saying, hey, there was a failure, and it can handle it in a variety of ways, depending on how you want to do that. So you could retry, you could kill the actor, create it again, and send it the message again. You could restart a variety of different actors if there were other things dependent on it. So it's pretty flexible and how you can handle that. So first example, simple one. So I'm going to go over essentially how you would design tail if you were making it with the actor model. So there's always a root actor that supervises everything. Underneath it, you could have a tail supervisor that has a reader who essentially just has a file handle, reads in some lines off the file handle, passes a message to the printer saying, here's my file name, here's the lines to print. And it seems pretty mundane, right? It's pretty simple. This might even be how you would design it with OOP, right? You could have a tail class, printer class, reader class, right? And the tail composes the reader composes the printer, and there's just a bunch of method calls instead of message passing. But the benefit to doing it this way is that each of these units is its own process, and they're all running in parallel. So when this reader passes a message to the printer, it doesn't just stop executing or yield execution to the printer. It can keep on doing things while the printer is printing. So you kind of have a trivial way of getting parallelism from your system. And for people familiar with other languages like Go or Haskell or whatever, these are essentially green threads. You could think of it that way at least, like a Go routine or something. But the power of designing it this way, is that later, if you want to tail many files, you essentially just have this tail actor spin up a bunch of more readers per file. All those readers are still executing the same exact code, still passing messages to the same printer, and you just spin up way more of them. If one of them dies, the tail actor has a chance to respond to it and say like, okay, we'll retry a few times, back off, do whatever we need to do, right? But it doesn't actually affect any of the other running parts of the system. So this reader would be unaffected by a failure in this one. So we could, this is a good example of how the actor system is fault tolerant. A failure in one side of the system doesn't induce failures in other parts. So you don't have to wrap try catches around all these different parts of your code to make sure it doesn't kill your entire app, right? It's kind of works that way by default. And in fact, with many actor model implementations, the mantra is let it die, right? Let it crash. You don't want to code defensively. Instead, be very liberal with how many processes you make, right? Make lots and lots of actors for fine-grained units of work. It'll give you more parallelism and more fault tolerance when they fail. And more isolation when they fail, too. And so like if one of these files were on like a USB stick and you unplug it, this actor will crash, but we'll keep tailing the others. But since it's still retrying, if you plug it back in, theoretically, right, and it mounts in the same location, you could recover and continue tailing. So it's a good example of its fault tolerance. But this is a pretty simple one. Let's move on to a bigger example. So say you wanted to build Slack, right? Hypothetically speaking, you could make Slack this way, right? So you have a chat supervisor who basically looks after the channel manager, connected users, and active devices. Each channel will have its own actor, and these actors are cheap, so you can have millions of them running at the same time. There's no problem. And essentially, if a user is connected to our server, they're talking to an actor that's dedicated to them. And essentially, when they want to post a message in a channel, they'll hit some API that talks to this actor. The user's actor will send a message to the channel if they posted a message in, say, random. And then when that channel receives a message, it updates its state, adds the message to the bottom of the channel, probably goes out to some database, so it's not like ephemeral, or stores it on disk, however you want to implement it, doesn't matter. And then when it wants to notify the users, it has the PID, which is the process ID, essentially the address of the actor, and it can send a message to all the users who are currently connected with some active devices. So maybe you have a Note 20 or iPhone 10, whatever. And when a message is sent to a channel that you're in and you're connected, well, this actor will forward the messages along to the users and the devices of those users, and they get push notifications. And the cool thing about this is that it's trivially parallel. And all the concurrency is managed just through having an actor that owns that concurrently accessed resource. So channels don't have to have any locking mechanisms of any kind, right? Because it's at the end of the day, each actor is single-threaded, but that thread is a green thread, so it can be really efficient. And there's another benefit that's maybe a little less obvious. So the actor model gives you essentially parallelism pretty easily, and that's really nice. And you can have millions of actors. They're cheap. They're very inexpensive to spin up. But probably the less obvious but larger benefit is the fact that you have this. So these actors can be distributed across all these different machines in different data centers, different availability zones if you're on Amazon. And if you're using something like Erlang, which is an implementation of the actor model, Erlang has the ability for you to link up a bunch of different VMs, Erlang VMs, and they kind of act as a single cluster. And they maintain all those guarantees and benefits that you have with a single Erlang VM, and they within the cluster. So whenever we were not in a cluster, and this is all running on my laptop, right? The message passing happens inside the VM, and it's very fast, efficient. It's trivial, right? And the supervision also happens within that one VM. But once you have it split up, Erlang VMs know how to communicate with each other. They know how to do supervision, remotely, with remote actors on remote VMs, right? And you can essentially spawn work and processes on all these different servers trivially. And it's very, so it makes distribution easy. And that's sort of the killer feature, is that you get parallelism and distribution almost for free. And your code is structured exactly the same way. Nothing about this code is different than the version that runs on my laptop, right? So the cool thing about this is that you don't have to change a lot about how you write code to get all these benefits. So actor model is very nice. So now that we got a good overview of that, let's go over Statefun a little bit. Statefun is essentially the idea, I think, was to be sort of serverless on top of Flink, to provide serverless functionality on top of Flink. So the idea was you have some stream of events coming in to your cluster. The cluster has all the state. It has distributed Flink state and all the guarantees that Flink brings with it. And then what they do is they sort of divide up that state into functions, virtual functions that you control with your business logic remotely. So rather than you get an event and then you talk to your database, it's essentially like the event goes to your database and your database calls you. So your data and your business logic are completely separate. And not only that, it's not just the data, but the guarantees it provides are all kind of stored inside of Flink. All the fault tolerance guarantees are here, and your code just needs to worry about business logic. And so whenever an event comes in, Flink says, hey, here's your state, and here's your message. And then you do your processing, you do your work, and then you return to Flink, hey, here's my new state and any messages that I sent to other functions. And you get all the nice standard benefits that Flink provides, like snapshotting, checkpointing of state. So, and that's important later. So essentially, again, we kind of see this pattern, right? You have a function. Function can invoke other functions. Functions have state, but the difference in this case is that that state is managed by Flink, and it's persistent, durable, atomic state. And you can kind of guarantee exactly once processing guarantees with respect to the state. And then the other thing you have is fault tolerance, because Flink, if it detects a failure, will continuously retry and roll back state every time across the entire cluster, meaning all functions. So if one function passes a message to function A, passes a message to function B, passes a message to function C, if C fails, B and A's state are rolled back, and everything retries. So you get really good consistency guarantees that way. But then I guess the downside is if you have a bug, it'll just sit there retrying until you fix it, I suppose. So a good example of an app that people usually build with Flink is Wordcount, because counting in Flink is really easy because you have atomic state. So if you're building this with Statefun, you have generally you have an ingress function. You would have you would split the words out, right, by spaces, and then you have these little counter functions. And these counter functions are just a very small function with an integer of how many times we've seen this word. And so this splitter is essentially creating a new counter for every word it encounters. So if you think of it like an actor, right, it's essentially spawning an actor for every single word it needs to count. And then from then on, it talks to that actor every time it sees that word again. And so that previous state is restored, and it could just say, hey, increment, I saw this word. And all you have to do is add one, and Flink gives you the same exactly once guarantees that you're used to in this ecosystem. So this is sort of the benefit over the actor model, is that if while we're counting, something happens, there's a failure, the state of these counters is rolled back in lockstep with the offsets on Kafka for this topic, the sentences topic, and the counts topic. And the power of that is we don't have to be idempotent when we're modifying state. Because if we fail, our state rolls back. So rather than having to store a list of unique IDs for every request we get and deduping and all that stuff, we can just count and do the trivial thing. And Flink handles the nasty, stateful world around us. So the one thing you might be worried about if you're looking at this is what happens when you have millions of words or tens of millions of words? How does this scale? You can't have this many actors running normally, right? Well, the cool thing about Flink functions is that they are virtual. So essentially, creating a new function is just creating a new state data structure inside of Flink. Because this state of each function is completely separate from the code and business logic that actually executes, Flink essentially has everything that you need to resume execution of your function. So when it's not executing, it's just sitting here on disk because they use RocksDB backend, right? So your function essentially gets swapped to disk when it's not being used. So when an event comes in, you have a key attached to it. And the Flink worker only has to go look up with RocksDB and say, hey, for this key in this function, give me the state. And it will go take that state, pass it the message that it was given on Kafka, and simulate all the function calls, essentially. And when it runs into a function that's the user's, like on the user side, it does a remote HTTP call to your user's API. And the user gets the state plus the event, mutates the state, does all sorts of message passing, and then sort of gives Flink the result of what it would have done and says, hey, I changed the state to be this now. I pass messages to these functions, and now go do it. And so the user API actually doesn't have to do a whole lot. It sort of just tells Flink what to do after the fact, right? And just executes its business logic otherwise. So it can be in any language too. So for any language that you have a Flink SDK, Flink Statefun SDK, you can implement stateful functions. So, and those functions can communicate with each other within the same cluster. So you could have a Python service talking to a Scala service all within the same Statefun cluster. And that's really, really powerful. So you might be wondering then, well, when should I use, Statefun or Erlang? And basically, for Statefun at least, if you need polyglot support, right, that's a good use case for Flink. For example, if you have machine learning models, right, and those are written in Python, well, you could have the rest of your backend code written in Scala or whatever language you like. And then you just pass messages to the Python models. They run. They can have their own state. They can be completely abstracted from the rest of the engineering team. And the data scientists sort of have the freedom to do whatever they need to do. And they just have to use the Flink Statefun SDK, and we're good to go. And another important thing is your app. It's more useful when your app is mostly reliant on internal Flink state. Anytime you interact with externals, even like Postgres or anything, everything you do has to be idempotent, because if Flink retries, you need to be able to retry. You can't commit. You can't commit to Postgres and Kafka at the same time, right? You don't have two-phase commits or anything. If you need atomic state, Flink is really good at that. That's sort of its key selling point for me, is that it can make normally really hairy code very simple because you have that atomic state synchronized with Kafka, right? And if you need large scale sharded state, so like there are lots of companies that run very large Flink clusters with terabytes of state, and they still process millions of events. It's not slow. It's still very fast. You can have massive Flink state and still be very efficient and quick because of how Flink works. You probably wouldn't want to use Statefun, I guess, for extreme low latency, like real-time applications, because there's lots of overhead, I guess, right? There's lots of HTTP calls being made, and you got to wait for checkpoints sometimes if you're using exactly once. And it's not going to be like super, super fast, right? At least not like the actor model is. But it'll have very high throughput. If you need replay, so replay is pretty powerful if you find out you have a bug and you've designed your app such that you can replay. You could potentially restore a save point from last week, replay through all the events on Kafka, and retroactively fix your bugs, right? And the other thing is, you probably won't want to use it if you need easily queryable state. So like if you're used to something like SQL, there's no like data grip for Flink State for going in and sort of querying it arbitrarily ad hoc, seeing everything, and even editing it, right? That could be a little bit of a pain point, but there are people actively working on this, trying to make it better. So lots of promising work going on there, but for the time being, right? For Erlang and Elixir, which are, some of the popular implementations of the actor model, it's really good for very low latency, like real-time applications. It has a great scheduler that can detect, it's very fair. So if there's one process that's just stuck in an infinite loop, right? None of the rest of your application should slow down or die unless it's, unless there's like tons and tons of them. It has a preemptive scheduler, so it can essentially be very, very fair and give other processes lots of time to execute as well. Long-running background processes. So this is something that's sort of a little bit more difficult to do in Statefun. Is in the actor model, actors are essentially processes. And so they can just stay in the background running for days, months, years, right? But with Flink, with Statefun, it's sort of supposed to be a short atomic units of work, right? Flink hits you with a request, and then you return back, oh, here's my new state. So you don't have time to sit there and process for like hours, right? Because you're blocking Flink checkpoints in the meantime. So you can work around this by like making it breaking it up into steps and then sending yourself messages, but it's not as convenient as like Erlang, where you could just spawn a process and just leave it. If you have lots of blocking work, blocking IO, compute, right? It's probably going to be a little bit more convenient in Erlang. In Statefun, again, while you're blocking, Flink is waiting for you. And in the meantime, it can't checkpoint. So that could be pretty bad. Fine-tune controls over where work runs. So like if you have an Erlang cluster, you can essentially say, okay, I want to run this process on a memory-optimized machine. You could have this process running on whatever machine. Right? You have pretty fine-tuned control over what runs where. And it's really good about that. Usually when you're using Statefun, though, you usually have like a load balancer, so it's just kind of getting distributed amongst the machines. You can still break things up and have certain functions run on certain servers, but it's probably a little bit more fine-tuned control with Erlang. And it's also less opinionated. It's lower level, and so it's a lot more, I guess, flexible, but also you have to manage more. So finally, how does Bluechip use Statefun? So our main project is the direct mail project where we send postcards to customers. I'll just kind of breeze through this a little bit. We essentially have a topic full of leads. They get sent through this pipeline that essentially is a cascade of functions that we call. So there's like address validation. There's a bunch of filters that use Flink State a lot. And a lot of it relies on the fact that Flink State can be expired, right? So if we want to filter something out, we can just set a Boolean to true, expire in 30 days, right? And we can say, okay, if we've mailed them in 30 days, which we know based on an activity topic, filter them out, equals true, for 30 days, and then it expires, and then we can mail them again. Then we buy some extra lead data, run a machine learning model. So this is Python. The rest of this code is Scala. And so we were able to let our data scientists essentially just consume the Statefun Python SDK. They use the state to store their models, I believe, and they can swap out those models in runtime, right, on a different topic. And then we essentially give it a score, and we upsert it into a batch in Mongo. And as a separate background process, periodically we pull our top in leads out of Mongo and send them postcards. So there were a few pain points, mainly the address validation and buying lead data. These were hitting APIs, and we didn't know about the whole blocking IO issue when we first started with this. And so these quickly became a problem, and we had to essentially do RPC over a different Kafka topic so that the HTTP requests were just handled by a separate service, not within Statefun. Ideally, it would be better if eventually there was a way to just do non-blocking HTTP requests within Statefun, like if there were some native function that we could send a message to and it would do the HTTP request within Flink. But yeah, Statefun is still, it's very active, and lots of people are really brilliant people working on very cool features for it. So I'm excited to see where that goes. So our plan, and then we also plan to use it for fraud. So fraud detection. So obviously, right, we keep lots of counters of different things that we care about. And if we see something go over a threshold, we can be like, okay, this might be fraud, right? And there's lots of things we can do with Statefun because of that exactly once processing. So then I want to move on and try to do a demo now, if I can. So I don't think I have enough time to go through actually writing all the code live. So I'm going to go over this example that I have on GitHub. I'll put the link in the slides so that you can find it later if you need to. But it's part of our open source Statefun 4S SDK that we made at Bluechip. Essentially, this is using our typed API, which is still a little experimental. We're still testing it out, but we've had pretty good luck with a few examples that we're trying it with. So I'll just kind of explain this example. So if you want to see the high-level view of how everything communicates, the best place to go is look at the module YAML. And this is essentially what you give Flink, and this generates the Flink DAG, which becomes the Flink job that executes and calls out to your API. So you essentially define all your functions. Here, they have a convenient globbing pattern now where you can essentially say any function that starts with example / goes to the Scala API. And then you can say anything that starts with scoring / goes to the Python API, right? And you can adjust this to try to keep blocking work from backing up Flink. Then for your egresses, I have Kafka here. We have a string input, which is being forwarded to the greeter entry function. And for our egresses, we have everything configured to be exactly once. Whoever sends the message to the egress function, this function ID, can actually determine what topic it goes to, what the key is, everything. So that's all pretty configurable. You only really need one egress. So first place to start would probably be the models that they use. So this is the models that the functions use to communicate, and also for their state. So the state is usually stored in some serializable structure. I'm using JSON here, but you could also use protobuf. Doesn't matter. We support both. So the greeter, the function that actually does the counting, will receive this greeter request, and it'll have a name to count, and it will reply to the address that's handed to it. The greeter response is what it sends, as a reply. The state is the number of times that we've seen that name. And the greeter RPC essentially is the function that's orchestrating the work. It needs to be able to receive a union, right, of multiple types. So we're using a seal trait here. It receives strings off of Kafka, and it receives a greeter response back from the greeter function. That'll make more sense now when you look at this code. And if you don't write Scala or don't know Scala, I'm sorry. I'll try to explain it as best I can without relying on Scala. But essentially, this is the greeter entry function that the ingress forwards to. And you can see it's example/greeter entry, right here. And that identifies it within the Flink cluster. We also map our input types. So we're either going to get a string or a greeter response, but our function has to take one type. So we actually make mappings here to unify it to a single type greeter RPC. We have to type in here because type inference isn't working well here. It's not widening the type properly. So we essentially just match on it. And if we're getting a request off of Kafka, it's a string. And we call out to our other function. So this is like message passing. Probably looks similar to like Akka, where you say ask when you expect a response, right? And we pass the first argument as the ID of the function. So this is the first time we're seeing this person's name. We essentially, it creates a new, you could think of it as creating a new actor, right? It's like spawning. And then if it's not, then it restores the previous state and continues. So the message we're sending to it is a greeter request, which has the name, and ask actually takes a function for convenience and lets us fill in the reply to address of this function automatically. So in Scala, you can just put an underscore and it turns this into a function that accepts one argument. Kind of convenient. And so it'll send off a greeter request to this greeter function. And you can see based on the type signature that this function accepts a greeter request as an input. It also uses greeter state as its state structure and responds with a greeter response. And one cool thing about what we've done here with the macros is we can actually check at compile time. When you call ask, we can check at compile time. Do you have a mapper for handling the response you're going to get? Right? Because that can be a really common runtime error. You don't want to happen, right? So if you send out a message to an actor, you're not expecting a response, and you get one, everything blows up now, and that's really difficult to recover. It's annoying to recover from. So here, if I actually comment this out, you'll see we actually give you a custom error message saying the calling function needs an input mapping for greeter response. To be able to call this function, you have to be able to handle its response. And that's all handled at compile time. So we kind of have a little bit of a sanity check there. And when we get our reply back, it will be wrapped in the response because of this mapper, right? So we take this response, we send it off to the printer. There's only one printer. We're thinking around different ways to handle singleton actors, but for now, you just hard code a string. We'll probably add annotations for it later to just customize the send function to only take one argument to enforce some degree of consistency there. But for now, this works. And then we send a function to our greeter egress, which uses our untyped APIs to pack a protobuf any message with a Kafka producer record, which Flink will use to write out to Kafka when it's committing offsets and everything. And then once you get to the actual logic of counting, it's just this. So to access the state and increment it, we can essentially just say, okay, inside the context of our function, take out the number of time, take out the count, whatever the current count is, add one to it, modify the context which is this greeter state structure, to have the new count. And then we respond with this greeter response message with the count in it. And we reply to our reply to address. And this is actually type checked. We have to return a greeter response, right? Because that's what we said we would return. And that's it. We yield, or we're done here. And then the printer just prints every message that comes into it. So why don't we go ahead and try to run this? We have a little Docker Compose here. Just spins up a Kafka Zookeeper, Kafka Broker, Flink Master Worker, and the Scala Worker. So let's go ahead and do this. Well, spoilers. All right. So we assemble our jar. Then we run it. Well, let's make sure we run Docker Compose down. And then run. All right. So let's open up Conductor, connect to Kafka, check out our topics. There they are. Start up a producer. And we start giving it names. So let's give it the value Tim. We're only going to send one for now. And there we go. We got a greeter response. Tell Tim one time. Let me subscribe to this topic. The greets are coming in. Produce another one. There we go. It's coming through. It's all JSON. It's keeping track of the counts. I can change it to be whatever. Bobson Dugnut. There we go. And you'll notice that it's actually pretty quick. Has some good throughput. We'll send 500 records at a time. And it's pretty quick. It's definitely not slow. Before you can really stop to think about it, it's done processing. So it's pretty quick, it's convenient, and gives you a lot of features and fault tolerance out of the box. Lets you not worry about a lot of things. Overall, I think it's a promising ecosystem, and I think it's got a bright future ahead of it. So that's all I got. Thanks, guys.